Well, how did you do with this question? This is a bit of a tough one. So what do we know? We know that the charge on the plates doesn't change. The significance of that is that since the E field strength in the regions where there is a non-zero E field is proportional to Q because it depends on the charge density, and that didn't change. And so the E field in these regions didn't change, but we know the E field is zero inside the slab. Okay, that E field is the slope of the V versus X graph. So before we put the slab in, we just had a straight line like this, and there's our potential difference across the capacitor. But after we put the slab in, we know that the field is the same in the regions with field, and so the slope of the V versus X graph is the same there, but then there's this big region in the middle here with zero field, and so zero slope of V versus X. And so you can see that after we insert the slab, the potential difference across the plates has to be decreased. By the way, I told you that the charge on the slab, on the surfaces of the slab, must be the same as the charges on the plates. How do we know that? Well, there are a lot of ways of seeing it, but an easy way is to draw a Gaussian surface. If you draw this Gaussian surface here so that this face is inside the slab, and this face is inside the plate, those are inside conductors, and so the E field at those two faces is zero. These faces are parallel to the field, and so the flux through them is zero, and so the flux through this Gaussian surface is zero. And so the enclosed charge is zero, and that tells you that the charge density here on this piece of the slab has to be the same as the charge density on the plate, and so their total charges must be the same since their areas are the same. Well, note that when the capacitor was connected to the battery, if we inserted the metal slab, then we increased the E field and increased the potential energy stored. Similarly, if we move the plates closer together, we increase the E field because we have the same delta V over a smaller distance, and so again we will have increased the potential energy. And so one might ask, can't we just put the plates arbitrarily close together and store an arbitrarily large amount of potential energy in any capacitor? Wouldn't that be nice? Well, unfortunately not, because there's a limit to how large we can make the E field between the plates. And that's because if the E field between the plates gets very strong, then it will literally rip electrons out of the atoms in that region. And so if you have air between the plates, what you do is ionize the air. Once you ionize the air, it conducts, a spark jumps from plate to plate, and charge will flow through the ionized air, and we're no longer storing charge on the plates. We're conducting charge from one to the other. This is called an electric breakdown, and it's exactly what happens anytime an electric spark jumps from one thing to another. The most dramatic example is lightning. And we call this electric breakdown. The breakdown E field of air is around 3 × 10⁶ volts per meter. And so if we exceed that, we will simply not store charge on the plates because we'll get a spark jumping. And by the way, this doesn't just happen for air, this happens for any material, although the breakdown electric field is different for different materials. And for example, in a plastic, breakdown can occur and a spark will jump through the plastic, melting the plastic and destroying it in the process. However, there is a way to increase the amount of potential energy we can store in a capacitor, and most real capacitors use this. Think of a capacitor which has nothing in between the plates attached to a battery. There will be a particular field inside it. Now, let's put an insulator, like the paper that I demonstrated with in between. What will happen is that the insulator will polarize. It won't polarize as much as a conductor would, typically, but it will polarize. Now, inside it, there are two fields. There's the field due to the plates, and there's a field pointing the other way due to the polarization of this insulator. However, the total field has to be the same as it was before we put this insulator in here, because we haven't changed the plate separation and we haven't changed the potential difference because the plates are connected to a battery. And so the total E field can't have changed. Well, that means for the total E field to have remained the same, even though there's now this E field due to the insulator opposing the E field due to the plates, that means the E field due to the plates must have got stronger. And the only way that can have happened is if more charge flowed on to the plates when we inserted this slab of insulator. This slab of insulator is what we call a dielectric. And it's serving several functions. One is that it's causing more charge to collect on the plates of the capacitor for a given potential difference across the plates. But also, most dielectrics will have a higher electric breakdown electric field than air will. And so we can push to higher fields without breakdown occurring, and also store more energy in the capacitor that way.